Okay, so what we're going to cover today, guys, are what we call the basic integration rules. So what we're doing today is what's going to make our lives a lot easier when it comes to integration. So what we're going to think about real quick is if you were given the fact that f prime of x equals 3x squared and asked what function f of x had this derivative, what would you say? What is f of x? If f prime of x is 3x squared, what could f of x be? So if you can't immediately think of one, pause the video and take a moment to think about it. I think that f of x could potentially be x cubed. If I take the derivative of x cubed, I bring the 3 down, subtract 1 from the exponent. However, that's not the only thing that f could be. F could be something like this. It could be x cubed plus 5, because when I take the derivative of 5, it just goes away. It becomes 0. F of x could even be something like x cubed minus 100. That's a very different function, but if I take the derivative, that minus 100 just goes away. So in reality, what's happening is f of x could be anything x cubed plus some constant. F of x could be any x cubed plus some constant c. If you take the derivative of this, you will get 3x squared. So there's actually an infinite number of possibilities of what f could be. So what we have here, this f of x, this is called the antiderivative of f prime of x. Antiderivative. Derivative, okay. So this is the day that some of you have been waiting for. Somebody in class mentioned, can we go backwards? So this is exactly what we're doing today, is we're going backwards with differentiation. We're going to start with f prime and figure out what was f, because that is what an integral is. So the symbol, just the integral of g of x d of x, we say that that is the antiderivative of g with respect to x. So from yesterday, we know that integrals and derivatives are very closely related with our fundamental theorem of calculus. They're very closely related. If you take the integral of a derivative, you get back to the original function. So all of our integrals, for them to mean something geometrically, they have to have bounds. They have to have numbers, a and b. So what this is an integral without limits. It does not have limits. We call it an indefinite integral. An indefinite integral, and it does not necessarily mean the same thing. This is not necessarily the area under a curve, because to find the area under a curve, we have to have bounds. We have to know it has to be bounded from what value to what value. So when it doesn't have limits, what we consider this to be is just the antiderivative. So this whole thing just stands for the antiderivative of g, going backwards in differentiation for g. So we're just going to be finding a lot of antiderivatives now. So we've got some 3 specific rules that we need to think about here. So if our function is 0, if we want to think about what is the antiderivative of 0, basically we want to think about what function, when we take the derivative, do we get 0? And what that is any constant, any c. So we use c for constant. Any constant function, if I take the derivative, I get 0. Okay, so what about if I have, instead of 0, I have another constant, I have k. So k is not a variable, it's just some number in there other than 0. So k would be, the antiderivative of k is kx. However, it's not just kx, it's plus c. So think about taking the derivative of kx plus c. The derivative of kx is just k, and then the plus c would be 0. So if you take the derivative of the right-hand side, you would get the part that's inside the integral. All right, so this is a big one. This is the power rule. This is if you have x raised to a power. So for derivatives, we're used to if f of x equals x to the n, f prime of x equals n to the x raised to the n minus 1. So integrals are going backwards. So I know that when I take a derivative, I subtract 1 from my exponent. So when I take an integral, I'm going to need to actually add 1 to the exponent. And then what I'm also going to do is I'm going to divide by that same exponent. And then we always have to have a plus c because there could be some constant on there that we don't know what it is. But when we take the derivative, it disappears. So I want you to think about this right here, the x to the n plus 1 all over n plus 1. Think about taking the derivative of that. What you would do is you would bring that n plus 1 down, and it would end up canceling out with the bottom. So you would have n plus 1 over n plus 1, x to the, if you subtract 1 from the exponent, you just get n. Okay, so that fraction cancels and you just get x to the n. All right, so we're going to see how this all works. So here for a, we have 3x, and this is really 3x to the first. So we have an x in here, so we're going to use the power rule. Anytime you have x, you're going to use the power rule. If I have a constant, a coefficient, I can just bring that out front. That's one of our properties of integrals. It'll just stay there, just like with derivatives. If you have a coefficient, it doesn't affect anything. It will just stay there and be present in your derivative. So here, I'll have 3 times the integral of x. So I'm going to add 1 to that exponent, so it'll become 2. And then I'm going to divide by 2. And then you have to add c. So this will become 3/2 x squared plus c. If you are unsure about your antiderivative, you can always take the derivative and see if you end back up at what you started with. And if I take the derivative of this, I will end up with 3x. Okay, for b, when we have multiple terms, we can just take the antiderivative of each term. So here, this is just going to be 3x. I'm going to add 1 to my exponent and then also divide by that same number. Okay, then I'm going to, for the next term, this will be 5x squared, add 1 to the exponent, divide by that. I'll have 4x. If I take the derivative of 4x, that gets me 4. So that's from this rule. And then I always have to have plus c for my indefinite integrals. If I'm finding the antiderivative, you always have to have plus c, because we could tack on any constant to the end. So this will become x cubed minus 5 over 2 x squared plus 4x plus c. Okay. Here, I'm going to rewrite this one as x to the negative 3 dx. So what's going to happen when I add 1, this will become negative 2 all over negative 2 plus c. I'll move that back down to the bottom. So it'll be negative 1/2, negative 1 over negative 2x squared plus c. For letter D, I'm going to rewrite this as x to the 1/2. So we're trying to find the antiderivative of x to the 1/2. So we are going to still keep adding. We're going to add that 1 to 1/2, so we'll get 3/2, and then we'll also divide by 3/2. So when I divide by 3/2, it's really going to flip that fraction. So we're going to be 2/3 x to the 3/2 plus c. All right, F, this is a little complicated. A way to make this less complicated, however, though, is if I'm going to think of the cubed root of x as x to the 1/3, and I'm going to distribute it out. So I'm going to distribute out before I take the antiderivative. So this will be x to the 4/3 minus 4x to the 1/3. And now I'm going to take the antiderivative of that. So 4/3, I'm going to add 1 to that. That'll be 7/3 divided by 7/3 minus 4 x to the 4/3 when we add 1, divide by 4/3, and then plus c. So I'm going to flip my fractions that are on the bottom. When I flip the second fraction, the 4's are going to end up, they actually cancel out. So I just have minus 3x to the 4/3 plus c. So I'll end up doing a similar thing here. I'm going to separate all of this out. This will be x to the 3rd minus 5x, and then I'll write this as 7x to the negative 2. And then I will integrate or take the antiderivative of each one. This will be x to the 4th. Add that exponent 1, divide by the same exponent. Again, we're dividing by that exponent because if I took the derivative, I would end up bringing that 4 down, and I would want it to cancel out with the 4 on the bottom, so that it ended up back at x cubed. Then I'll have minus 5x squared over 2. And then I'll have, so for the 7x, so this is going to be x to the negative 1, plus 7x to the negative 1, and then I'm going to divide by negative 1. Making sure I had plus c on my other ones, plus c. So this would be, you can leave it as x to the 4th over 4. You can write it as 1/4 x to the 4th. Either way works. I'm just going to rewrite this third term as negative 7 over x. All right, here we have a fraction again. We don't have any rules about fractions, so I'm going to split it up. This will be x to the 1/2 plus x to the negative 1/2. If at any time you need to pause the video in order to process some of the algebra, please feel free to do so. So now I'm going to take the antiderivative. So once I take the antiderivative, that's when my integral sign goes away. So I'm going to add 1 to each exponent, be 3/2, divide by 3/2. When I add 1 to negative 1/2, you get 1/2. And then plus c, always. This will be 2/3 x to the 3/2 plus 2x to the 1/2 plus c. And we can leave it like that. Last one on this page. So again, I don't have any rules right now about an inside function versus an outside function. So what I'm going to do is I'm going to FOIL this out. And if I FOIL it, I get t to the 4th plus 2t squared plus 1. So again, I haven't taken the antiderivative, but now I'm going to. So t to the 5th divided by 5 plus 2t to the 3rd divided by 3 plus t. So remember, any constant, when you take the antiderivative, you will add a variable onto that. And I just noticed that this is dt. So this is just taking the antiderivative with respect to t. I think all the other ones were x. And then plus c. I'll leave this one as is. Okay. So that's just practice using those basic rules. Here's a more conceptual question. If we're given that f double prime of x equals 3, so that's the actual function, is 3, and then we're given specific points of f prime, we're given f prime of 2 and f of 2, we want to find what is the function f of x. So what we're going to do here is I know that f prime of x is the same thing as the integral of f double prime of x dx. And I'm actually given what f double prime of x is. That is 3. And I can find the antiderivative of that. That would be 3x plus c. So I know that f prime of x equals 3x plus c. So what I'm going to do now is I know I'm going to use the fact that f prime of 2 equals 5. I'm going to use that to figure out what c is here. So if I plug in 2 to this function, I know that that equals 5. So 5 equals 6 plus c, so c here is going to equal -1. So that tells me that f prime of x equals 3x minus 1. And now I'm going to do a similar process. I know that f of x equals the indefinite integral of f prime of x dx, which is the integral of 3x minus 1. Go down to the next line. I know that that's going to be 3x squared divided by 2 minus x plus c. Okay, so here I need to find what c is. So again, I'm going to use this piece of information I've been given, that f of 2 equals 10. So I'm going to do f of 2. So I have 3 halves times 4 minus 2 plus c, and I know that that equals 10. That cancels out. So we have 10 equals 6 minus 2, which is 4, plus c. So 10 equals 4 plus c, so c equals 6 here. So final answer is f of x equals, I'll do 3 over 2 x squared minus x plus 6. So that's just a little trick using antiderivatives. Okay, so this table below shows some antiderivatives or indefinite integrals of trig functions. So it would be good if you paused the video and took a look at these and tried to figure them out yourself. So for instance, the first one is, what can I take the derivative of to get cosine of x? So here, this is actually going to be sine of x. So if I take the derivative of sine of x, I get cosine of x. You cannot forget plus c though. Let's think about the next one for the integral of sine of x. So I know that if I take the derivative of cosine of x, so let's think if I take the derivative of cosine of x, I get negative sine of x. However, if I made this negative, if I take the derivative of negative cosine of x, you'll get negative sine of x, and it'll become positive. So it's negative cosine of x plus c. So whereas sine, the derivative of sine is positive, the integral of sine actually is negative. So it's the opposite. So it'll be similar for, here we have cosecant squared of x is going to end up being negative cotangent of x plus c. Secant squared of x is tangent x plus c. Next line is going to be negative cosecant of x plus c. And then the last one is secant of x plus c. So you can look at all of these and see how if you took the derivative of the right-hand side, you'd end up with the function inside the integral. So we can use these then to evaluate each of these antiderivatives. So this 2, I can just bring it out front. So 2 times sine of x dx. So this is going to be 2 times negative cosine of x. We'll do plus c. So this will be negative 2 cosine of x plus c. So you can distribute that 2 to the c, but c is any random constant. So it doesn't really matter if it's c or if it's 2c. It's still just a random constant. All right, this next one. I don't know how to evaluate this quotient, but I bet if I play around with it, I know that sine of x over cosine of x is something that's tangent. And I can do 1 over cosine of x. And then I still have exactly what I had in the first integral. So this is the same thing as integral of tangent of x, secant of x. Okay, so what can I take a derivative of and get tangent of x times secant of x? And that would be secant of x plus c. All right, our last two basic rules are with our e to the x function. E to the x is great because if you take the derivative of e to the x, it's just e to the x. Same thing with integral. If you integrate, find the antiderivative of e to the x, it's just e to the x plus c. 1 over x is a little bit different. So if you remember, if f of x is ln of x, f prime of x is 1 over x. Okay, so we can go backwards. Notice, however, that one thing is a little bit different. We have the absolute value here. That's just making sure that we're not putting in any negative numbers into ln, because we always have to plug in positive numbers. So the absolute value sign just makes sure we are in the correct domain. If you tried to use the power rule on this, so this is 1 over x is x to the negative 1. If you try to use the power rule and you add an exponent, it would be x to the 0 divided by 0. And that doesn't work, and you'd get stuck. So it's good to recognize that 1 over x, if you have that in an integral, that really means you have ln. Okay, so for a here, this is just going to be 5e to the x plus c. This one's just going to be 5 ln of the absolute value of x plus c.